So we move on now with Coralie Neiner. She will talk about Magneto-asteroseismology of Hot Stars.
So before I speak about magnetoasteroseismology, I would like to remind you what we know about magnetism in hot stars. And what we know is mainly thanks to Padon at CFHT. We know that about 10% of hot stars are magnetic, and the magnetic field at the surface, at the pole of this star, is typically 3 kilogauss, but it varies from a few hundred gauss to a few tens of kilogauss. These fields are very simple. They are usually just dipoles that are inclined compared to the rotation axis of the star. And they are very stable in time because they are fossil fields. That means that they are fields that were there when the star was formed or that are coming from a previous phase of the star, like a binary merger, for example. They are not generated by the star. In addition to this fossil field that we see at the surface of the star can also have a dynamo field in the convective core, but we don't see those dynamo fields at the surface. They cannot reach the surface. Now, there are still a lot of things that we do not know about magnetism in hot star, and in particular, the role of magnetism on the internal structure, on the stellar evolution, or on the circumstellar environment of the star. We don't understand the interaction between the magnetic field and other physical processes, but there are predictions by theory. For example, the interaction between the magnetic field and pulsations. We know that the magnetic field, according to theory, should decrease the stochastic excitation of pulsation in the core, but should increase the pulsation in the envelope. It should also modify the internal structure of the star because it changes the region of the excitation of these pulsations. It will change the position of the instability strip in the HR diagram, as Keegan-Thompson Parison showed for Delta Scuti star just before the coffee break. The magnetic field will also modify or completely suppress certain mode, in particular higher order G mode, and it will modify the curvature of the period spacing of pulsation. It will change the position of the dip if there is a dynamo field, etc. So the magnetic field provides a lot of diagnostic for the internal structure of the star and physical processes inside the star. And in particular, it also allows us to measure the internal magnetic field that we cannot see at the surface. Now, these are examples of the impact of the magnetic field on pulsation, but it also affects all the other processes. For example, it rigidifies the rotation, it inhibits the mixing inside the star, etc. So to answer all these questions, what we should do is magnetoasteroseismology, that means seismology using pulsation to probe the internal structure of the star, combined with magnetic information. And this has been done for only a few hot stars so far, but the first two, Beta Cep and D22 for those stars, it was not a full magnetoasteroseismic model. We were just using some information of the magnetic field to try to constrain or select the best seismic model. But for the third star here, HD 43317, it was possible to do a full magnetoasteroseismic model for the first time. This is a hybrid pulsator, a Beta Cep and SPB pulsator, and it was observed by CoRo during 5 months consecutively. And what you see on the right figure here is the frequency of all the pulsation detected in this light curve. And you see that there are a lot of pulsation detected, but they are all low radial order G mode. There are no high order G mode. And I just told you that theory predicts that the magnetic field should suppress this high order G mode. So this was a hint that maybe this star is magnetic. We performed forward seismic modeling for this star, and we also found that there is no mixing in this star, which is also a hint that there is a magnetic field in this star. So we observed it in spectropolarimetry. You see on the left that we detected the Zeeman signature of the magnetic field here. I hope you see my mouse. And we found that the magnetic field at the pole at the surface is 1.3 kilogauss. So using all this information, the structure that we had derived from the forward modeling, the fact that the rotation should be rigid because the field is strong, the rotation period we derived from spectropolarimetry, the field topology at the surface also from spectropolarimetry, and the fact that there is no high order G mode, but other G mode present, we were able to do a magnetoasteroseismic model of the star and deduce that the magnetic field near the convective core should be about 450 kilogauss. This was the first indirect measurement of the magnetic field inside a hot star. Of course, we would like to do this on many more hot targets so that we can get a more global view of the internal structure of hot star and how it changes with evolution, for example. And so for this, the first step is to identify magnetic pulsating stars. And this we know how to do. We can use indirect indicator, in particular, the fact that in the light curve, we should see rotational modulation of the light due to the presence of the magnetic field. And if we use spectroscopy, we can also find chemical peculiarities that arise from the presence of the magnetic field. Once we know which target to observe, we need to characterize the field at the surface. And for this, we need a lot of spectropolarimetric observation. And we need to interpret this spectropolarimetric observation, taking the pulsation into account. And you can see how we do this in the poster by Chloe Guterich on her code PIMS. In parallel to that, we study the pulsation, either with a space-based light curve from Corot, Kepler tests, and so on, or from spectroscopic data taken from the ground. And there as well, when we interpret the pulsation analysis, we need to take into account the fact that the star is magnetic, because, for example, the magnetic field will split the pulsation frequencies. So you can misidentify the pulsation mode if you don't know that the star is magnetic. So when you combine these two kinds of analysis, spectropolarimetry and pulsation analysis, you are then set to make a magnetoasteroseismic model. So we're preparing for this model with a big observing program in spectropolarimetry, with Espadon at CFHT, of course, but also with Neonarval at TBL and Herbst-Paul at ESO. And we've selected two kinds of targets. First, the known magnetic pulsators. These are about 50 targets that we've already identified and confirmed to be magnetic. And we need to do the characterization of their field at the surface. You'll notice that there are no gamma doors in this group, and you will understand why in the talk of John Labadie-Bartz tomorrow. And the second group is the candidate magnetic pulsators, those that we have identified as probably magnetic from their rotational modulation in the Corot, Kepler, or TESS light curve, but we still need to observe them to confirm the field and then characterize them. We have several hundreds of these candidates, including 47 that will be observed as well with Plato in its first field of view after launch at the end of 2026. So when we want to do a magnetoasteroseismic model, we need to collect about 40 spectropolarimetric observations for each star that we want to model. And this is because we need to cover not only the magnetic phase as the star rotates, we need to observe the star under various orientation, but we also need to cover all the pulsation phases of each of the pulsation mode that is present in the star. And for this, we need a better coverage than for a non-pulsating star. So this is quite time-consuming. And I take the opportunity to thank the tax that I've already given quite some time to this program on PI time. But now we think that to really do several magnetoasteroseismic models of different type of star at different ages, different types of pulsator, etc., we need, of course, to go in a community survey. We cannot do this on PI time anymore. And this is why this is part of the Work Package 5 on stellar magnetism in the Amakihi community survey that was just presented. So to conclude, my main message is, first, it is essential to take magnetism into account when you want to study other physical processes in hot stars, and vice versa, you need to take these other processes into account when you study the magnetic field of a hot star. You cannot just do these things separately. Now we are doing magnetoasteroseismology of hot star. It has started. We have the test data already available to change gear and do many more models, but we need the spectropolarimetric data to do the characterization of the field at the surface to have those constraints for the models. Plato will be launched at the end of next year, and these Plato targets will be even better than the targets we had so far because they are brighter stars, so they are easier to observe in spectropolarimetry from the ground, and the Plato data will be really exquisite. So once we have done several magnetoasteroseismic models of different type of hot star, we will have very good constraint for stellar structure and evolution of hot star, which is, of course, our final goal. I will stop here, and I'm ready to take questions if there's time left.
Thank you, Coralie. Questions?
Thank you, Coralie, very much for a very interesting presentation. I have a small question about the theoretical research in the area of simulation of stellar pulsation in the presence of magnetic field. So are there any recent advances in this area that we can do this?
You're saying advances in modeling pulsations with magnetic fields? Yes, there are several codes that are being developed. So either for 3D codes of pulsations in stars, including rapidly rotating stars that are deformed. And there are also codes that are being developed for evolution of stars, including magnetic field. This is true for SESAM, SESTAM, and Star Evolve that are currently being modified to include a magnetic field. So these tools are being developed. They are better and better. Originally the magnetic field was relatively rough prescription in the codes, but it's getting more and more detailed, and we are getting better and better results.
Okay, so no more questions. So we move on. Okay, thank you, Coralie.
Thank you.
Thank you, everyone.